In the name of God, the compassionate, the merciful. Chapter Engineering Plasticity, Chapter 2, Stress Analysis, Part 2. Now then, we were talking about Cauchy's concept of stress, and we explained what the stress and internal stresses and stress at a point and stress at planes are and what we mean by them. Now we want to know what happens if we have a non-uniform internal stress system. For instance, we have this example where we have a irregular shape and we have many forces applied at different parts of this shape, and the magnitude of these forces and their direction also are all different from each other. So we want to know on a plane inside the body, we are considering what are the states of stress. Again, using equilibrium argument, because we say that this is under equilibrium, there will be some stress distribution acting on any given internal plane. So this is an internal plane. There are normal stresses applied due to the normal components of these forces, and there will be shear stresses applied on the surface due to the shear components of these forces. Okay? To evaluate these stresses is not a straightforward matter. Suffice to say that they will be invariably non-uniform over a surface. That is, the stress at some particle will differ from the stress at a neighboring particle. Obviously, because they have different magnitude and different directions, so at each point stress will be different, and it will be a difficult job to obtain the internal stresses and to have a precise analysis for such a problem. Now here in this figure we have shown a body of material, again in here, a body of material by its molecules or atoms. Molecules are shown here, and these small arrows showing the forces acting on each molecule. And as we can see, there are many thousands of forces acting on the molecules in the body of the body of the material, and these forces are at different directions, have different magnitude, and therefore finding the forces acting on the body or in the internal parts of the body is a difficult matter. Unlike some of his predecessors who attempted the extremely difficult task of accounting for all the molecular force, here we are talking about Cauchy, his predecessors, Cauchy's predecessors. Before Cauchy, many people attempted the extremely difficult task of accounting for all the molecular forces. However, Cauchy discounted the molecular structure of the matter. He said, forget about the molecular structure and look at it phenomenologically, okay? And simply replace the imagined molecular forces acting on the plane by a singular force F. So if you consider a plane inside the body, then these molecular forces may have a resultant like that on this plane. So instead of considering each of these and see what their influence is on this plane, we get the resultant of this, and we say that is the resultant of these molecules. If we take another plane in another direction, then the equivalent force to these molecules will be different. Now, after some introduction that we have talked about in previous slide, we want to get a precise definition for the stress. How do we get that? Now, supposing that this is a plane passing through some point in the material, okay? The materials that we showed you in previous slide, now we have taken a plane inside it. So this is a plane inside a material, and that's the point on which this plane has passed through. Okay, first define the traction at some particular point in the material as follows. That's the particular point in the material. We want to define the traction. What traction means? For instance, if you pull or push something, if you pull or push something, the applied force, we call it traction. Okay, that's traction. So we want to define traction here because it helps us to define the stress in a more precise manner. At some particular point in the material, take a plane of surface area like S. Okay, so we take a plane like S through the point on which acts a force F. So this plane is in a particular angle and the force acts on this point. Next, shrink the plane. Shrink the plane. Shrinking means making it smaller. Okay, so we make it small. We keep the scale in all directions for the force, for the surface and everything, but we make it smaller. Okay, shrink it. So we shrink the force and the plane all together. As it shrinks in size, both S and F get smaller. Okay, you see, we shrink it in size, so S becomes smaller, F also because it becomes smaller, so we call it delta S and delta F because they are infinitesimal. They are very small values. Okay, and the direction in which the force acts may change because we are shrinking it, so the direction may change. But eventually, the ratio of F over S, delta F over delta S, will remain constant. It reaches such a small value that obviously their ratio is constant because we have kept the scale constant. I mean, not the scale, the relative scales of F and S, we have kept them constant. Now, will remain constant and the force will act in a particular direction like that. The limiting value of this ratio of force over surface is called traction vector T. Okay, this is acting on the surface, it's pulling it, that's why we are calling it traction. And in the limit, as delta S tends to 0, we say that this is equal T, or traction. We call that a stress vector. That is the stress vector or traction. Okay then, so we have different traction vectors acting at the same points depending on the plane that we pass through it. For instance, we have passed through the plane like that. The normal to this plane is like this, but here we have passed the plane in that direction and normal is this. So that's N1 and that's N2. So the limit for this one, Tn1, is limit as delta S tends to 0, delta F over delta S. And here is the same, okay, in the limit. Now, after defining the traction force and how we obtain it in the limit, we are going to define the components of stress and traction. Now the traction vector can be decomposed into components which act normal and parallel to the surface upon which it acts. Okay, so this is the surface and that's the traction force Tn, and we say that we can resolve this into different components. Ijk are the unit directions at x, y, z, I, j, and k. And therefore, if this is t, k, we can have its components on the z, on the x and y axis as like that, ty and tx, and this is obviously tz. So these are the direction units, and then we can have vector, stress vector or traction vector equal to tx, its components in the x direction, times I, its component in the y direction, times j, component in the z direction, times k. And if we replace these tx, ty, tz by sigma, we can write sigma like this, sigma with two indices, zx, zy, zz. What are these indices? We have explained it here. Sigma ij, I and j are x, y, z. So we can have different components for sigma depending on which direction we are talking about. So sigma ij means that the first subscript, which is I, denotes the direction of the normal to the plane. So if we are considering, for instance, this plane, xy plane, then I would be z, would be k. Okay, I would be k, sigma k. And then the direction and the plane. And the second denotes the direction of the component. So j, which is the second indices, indicates the direction. For instance, if we are in the xy direction and we want to denote the stress in the y direction, we put for j equal to y. So if we are in the xy direction and in the y direction, we write this as sigma z y. Okay, so that's why here we have written tx as sigma zx, sigma z, because the normal is z, and x because in the x direction, and sigma zy, as I just explained, is in normal is the z direction, y is the direction of the stress, and sigma zz also because both direction and normal are in the z direction. Of course, in some books you will see exactly the opposite of this notation. Here we have said that the first subscript indicates direction of normal, but in some books you will see that the second subscript will denote the direction of normal, and the first subscript will not denote the direction of component. So, but this is customary, especially those books who have been written by mathematicians. Mathematicians usually take these indices as opposite to what we take in the engineering. Okay, so engineers take like this, but mathematicians take it the opposite. But don't be surprised if you see such a notation later on. Okay then. So these two components, as you see, are in the xy plane, and they are the shear components of this. The only normal component is sigma zz. Okay, so we have two shear components and one normal component for this stress vector or traction vector. Okay, Now, another concept that I would like to talk about is this Saint Venant's principle. What does this means? Now, in these figures, the first figure here, we see that we have a bar connected to the wall and it's fixed here, and there is a string or cable here which along which is applied a force on this bar. Okay, we can replace this with this, a simple model, F applied at the bar. However, if we want to see what are the internal forces, we have to cut it off by a plane normal to F or at an angle. Now we have cut it by a normal plane in here, and we say that sigma is equal to F over A on this plane, as we explained in previous slides. However, if you look at this place, very near where the force is applied, the real situation is like this, not like that. The forces are distributed like this. In fact, they are not uniform. So the distribution of stress near the point of application of the force is a bit complicated, sometimes very complicated. And therefore we cannot assume here sigma is equal to F over A, because this is for this kind of distribution of force. Distribution of force must be uniform to write down this. Otherwise, we should integrate, along the area. And that is a bit difficult, and for every application you have to do an integration and you have to find out how it is distributed, so it becomes a bit complicated. So this is a fact. But why we say that this is correct? Because it's away from the point of application. As you can see here also, the distribution of force away from the point of application of the force is uniform. Therefore, if we cut the bar by a plane like that, we can assume uniform stress, but in here we cannot. Okay, so that's the complication we have. What Saint Venant says is this, that in these two figures, it says that if we have a force like that, obviously the stress will be F over A at some point in here. But if we divide this into two equal parts, F over 2, F over 2, applied in the same direction, this is equivalent to this, obviously. Saint Venant says that its effect on the body also is the same. Otherwise, it means that the stresses are the same. It is an experimental fact that if two different force systems are applied to a material but they are equivalent force systems, then the stress fields in regions away from where the loads are applied will be the same. This is very useful principle because it helps us in real situations where a body is under complicated application of forces. We can simplify those forces and make an equivalent force system and use that equivalent force system to obtain the stresses in the body. So it's very helpful, a very important principle.